All right, good morning, everyone. So, as promised, here's a quick video talking about the group assignments. So here's the first one. So again, we talked about this in class, so I'm not gonna beat you on the head over it too much, but again, this is just kind of walking through what would happen if you were standing in a boat and then jump off of it to get the harmonic oscillation. So again, quick recap here of the pictures that we drew. So this is my fluid level. So in part A, it's just saying that I'm going to take my object and then float it in the fluid. So again, saying as cross-sectional area of A has a length of L to it, and it simply wants to know what is this amount here, H, at which this thing is floating in equilibrium. So this is part A. So again, here we're just going to say that some of the forces, let's say in the Y direction, are equal to 0, where this would be my Y direction. If I could actually draw a straight line. Anyways, so here, this thing has simply mg down in this direction, and then has the buoyant force pushing upward. So I think my buoyant force, the buoyant force is going to be, again, the density of the fluid times the volume of fluid being displaced times g. Good. Part B, we're now just going to apply a downward force to this guy. So now I'm going to have the same object, but now it's going to be submerged deeper. So again, now I'm going to be applying a force of F downward onto it. And this thing is now going to be submerged to a new depth, where that new depth is going to be this depth. Let's call that H prime, where H prime, as we talked about, is then H plus X. So that's the original amount here of H, and then plus this extra little bit here of X. And then finally, part C, all we're going to do is then take away that particular force so that this thing now will experience an upward net acceleration. So my acceleration then will be upward. And then from there, we want to no longer have the sum of the forces like in this one. So here again, the sum of the forces, say in the Y direction, are equal to 0, where again, this is going to be my Y direction. So again, the only difference here is now I have 3 forces, as we talked about in class. So I'm going to get an F buoyant force minus the applied force of F minus then the weight is equal to 0, but here now it's no longer going to be equal to 0. I now have the sum of the forces in the Y direction are equal to MA, and then I have all the other forces that are acting on it. So again, here, what I want to do is, as we talked about in class, get A then is equal to negative something times X. So I'm going to have to use my solution from part A into here to get it in this form. And then whatever shows up here in front of the X will be my omega squared by definition. From there, we'll just read off what omega squared is, and then use that to then determine what is the period. Great. So that's the first one. The second one, I know we talked about the second one in class as well. And let me bring that one up real quick. There it is. So this one is simply a physical pendulum. So here we're told that we want to find out the location where it needs to be pinned for this thing to harmonically oscillate so that it has a period of 2 seconds. So let's bring that up real quick. So basically, again, here is my thin rod. Right, there's my thin rod. This is going to be my pivot point. This would be then my center of mass. And then it's asking for this distance here. This is my X. Right? And then we're told in the problem that this thing has a length of L, which means my pivot point here is at a length of L over 2. Which means that this distance here is my distance D. Right, so if this side has a total length of L over 2, and then this thing is pivoted at a distance of X away from the endpoint, that means that D then is going to be the same thing as L over 2 minus X. So from here, you're just going to use the fact that, again, the period is equal to 2 pi divided by the angular frequency, and then use that to then determine what this X value has to be. So you have to solve a quadratic, but that's fine. We all know how to do that by now. I think that's pretty much about it. So otherwise, the only other thing we'll need is what we talked about in class is that, remember, the moments of inertia about some other pivot points is equal to the moments of inertia about the center of mass plus the mass of the object times the distance squared. So this is the parallel axis theorem. So yeah, that's that one. And finally, the last one, which we didn't get to talk about in class, but I'll talk about that guy now. This one involves mostly older stuff with a little bit of new stuff. It's there mostly to remind you that all this other stuff that we did a long time ago, which you did last session, is still true and valid. So forget about it. So basically what's happening here is that M1 is sliding to the right with an initial velocity of V0. It's then going to make an elastic collision with M2, causing it to bounce off, going back in the opposite direction with a new velocity of V1 prime. Meanwhile, M2 will pick up its own velocity of V2 prime, which causes it to then harmonically oscillate since it's attached to the spring of spring constant K, where it's going to harmonically oscillate, as it says in the problem, with a period of 0.14 seconds being attached to the spring with a spring constant of 1,208.5 newtons per meter. Meanwhile, M1, which is now sliding back in the opposite direction, will then encounter a little cliff here. So it's going to say come off a table, where that table has a height of, according to here, 4.9 meters. And it wants to know how far will it then land under projectile motion, the distance d, away from the edge of the table. So let me kind of scribble all that stuff down to our picture here. So again, initially, here is my table. Here is my mass M2 attached to the spring of spring constant K. Okay. Meanwhile, M1 is here, moving to the right with an initial velocity of V0. And we're told what V0 is and what M1 is, and etc. So what's going to happen then is these guys are going to make an elastic collision. So the next part then is it's going to look like here. So I'm going to get M2 here again. And then I'm going to have M1 hitting here so that under the elastic collision, this one's going to bounce off in this direction with a V1 prime. And then this one is going to start moving in this direction with V2 prime. Okay. After that, this guy here, M2, will be harmonically oscillating back and forth about some amplitude. And then M1 will then be moving again back in this direction with V1 prime until it reaches the endpoints here, where this thing is going to fall a height of h. So it's going to be right here, M1, moving again in this direction with the velocity of V1 prime, so that it will undergo parabolic motion and then fall and land on the ground down here, so that it will cover this distance of d. Okay. And from this, what I want to know is what's the distance d. So going back to the problem, the things we want to know, first of all, is what's the mass of M2? And then what is the velocity V1 prime after it falls off, or after it goes back in the opposite direction, I should say. And then again, what's the distance of D? So things to remember here. So first off, first thing we know is that what M2 has to be greater than M1. And the reason we know that is because M1 goes back in the opposite direction. So if you remember back from 175, what happens then is when two objects collide with each other, if M1 was greater mass than M2, then it would just bowl its way through M2, just causing M1 and M2 to go in the same direction. Just M2 would go faster than M1. If they were equal in mass, what would happen then is that M1 would stop. M2 then would carry on with the initial amount of velocity that M1 had, which means for it to go back in the opposite direction, M2 then has to be greater than M1, right? So basically for part A, we know M2 must be greater than M1. Okay? Now we can find M2 based on the fact that this guy harmonically oscillates with a period, and that period is 0.14 seconds, right? So this is basically the only new part of the problem. So in this one, you're going to use the period. Okay? Now the question is, which mass is actually harmonically oscillating? And that'll give you the mass that's going to be used inside of the period here. For the velocity V1, part B, we just have to use the fact that this is a one-dimensional elastic collision. So if you go back to 175, which you should have learned was that after a collision, elastic anyways, V1 then would be equal to the initial velocity of the first block, which in this case is what we call V0. times then what? M2 minus then M1 plus twice then M2 times V2 initial, all then divided by M1 plus M2. I got that backwards. Sorry. That's M1 minus M2. Sorry. Everything else is true. And then simultaneously, V2 prime would then be equal to what? V2 initial times then M2 minus M1 plus 2 times M1 V1 initial, which is what we call V0 in this case, all divided by M1 plus M2. So these are the most general solutions for an elastic one-dimensional collision. So here, since M2 is initially stationary, what that means is that V2 initial is simply equal to 0, which means that this term is going to be 0. So in this case, all we're looking for is what is the initial velocity of the first mass, which means we're just going to use that first equation. So just use that to then determine what is that initial or that final velocity after the collision for V1 prime. And then finally for part C, this is just to remind us how we do projectile motion. So remember projectile motion, the way that this would work is we'd have to set up some sort of coordinate system. Now again, coordinate systems don't matter. We can choose any coordinate system we want to. So for example, you could choose the traditional one. So you'd have y going upward, and let's say x going to the left in this case, it's moving to the left. Or I could choose that, for example, y would be downward, and then x would be to the left. Whichever way you want to do it, it doesn't really matter. And then we know that the acceleration due to gravity has to point downwards. So it's going to be the direction of g. So just remember that for projectile motion, all you would then have to do would be what? Write down the x components, and then write down the y components using our second kinematic equation. So in this case, I have y is equal to y initial plus v initial y plus 1/2 a yt squared. And in the x direction, I have x is equal to x initial plus v initial x times t. And since there's no acceleration in the x direction, I don't have to worry about that one. And then from whichever chosen coordinate system you would have, you would get rid of some of these particular values, or at least choose their signs. And then from there, since in this case, we're looking for something in the x direction, which is this guy, you would first have to use the y direction to find the time. And then plug that time then into the x direction to then find the distance x, or d in this case, where d is the time at which it has taken for this thing to fall the height of h. So that's pretty much it. So like I said, this problem is mostly just to kind of remind us of all these old things. So in part B, we're using conservation of momentum. Part C, we're using projectile motion with kinematics. Part A, again, is the only new part using all new information. Where in this case, we're using periods and harmonic oscillators and all that good stuff. So yeah, so again, just kind of work on all these things today. If you can, work with somebody else if they are group problems. If not, don't worry about it. Again, once you're done with them, just hang on to them. And then right before the exam, I'll put the hyperlink. You'll just take pictures of all of your work and then go ahead and upload those using the hyperlink. And then I'll count these towards extra credit for the exam. Otherwise, if you have any questions on these, if you're running into problems or you want to clarify things, go ahead and send me an email or ask me in class tomorrow, or stop by on office hours on Friday. And yeah, otherwise, work on these, get some practice using harmonic oscillation, and then I'll see you guys tomorrow in class to start talking about waves.